This is the next video in a series of videos about collision theory. We've now talked about the three facets of collision theory: frequency, orientation, and energy. We've talked about the effect of temperature on the rate, and we've seen the Arrhenius equation. So now we are finally going to get some data, and we are going to find activation energy from the data. So this is our Arrhenius equation. K equals A, the fudge factor, times e to the negative activation energy over gas constant times temperature. And you may remember how long we spent in the integrated rate law section of videos about trying to linearize every possible equation. So you won't be surprised to find that we are going to linearize this equation as well, because we are chemists and we find that equations are most useful as linear relationships. We bend over backwards trying to linearize our formulas so we can plot them as a line. All right, so we're going to linearize our equation. Make sure that's a lowercase k. Linearize our Arrhenius equation. Negative EA over RT. It's a clunky exponent to carry around anyway. I won't be sad to see it go. All right, so we're going to linearize this equation with one of our favorite tools, and that's the natural log. So we're going to take the natural log of both sides. We're going to end up with natural log of K equals, and then we're going to split up the activation energy over RT like this. So we're just going to write that one term with the little multiplication symbol in the middle, plus natural log of A. And those all use the natural log rules. So now that we've taken the natural log, it has split this exponential multiplication term into two separate terms, and it's brought this big chunk out of the exponent. So now if you squint, you can see the equation for a line. The y is going to be natural log of k equals m. The slope is going to be negative activation energy over r. We're going to make 1 over temperature our x value, and our y-intercept is going to be natural log of A. So we aren't really going to care very much about the natural log of A, but we see here that we're going to have to do transformations to two of these kinds of data. So let's pull up some actual data to look at. Here is some actual data. I'll give you a second if you want to write that down. Okay, so we are going to find the activation energy from data. So the kind of data that we need to collect needs to be data that relates to the variables in the Arrhenius equation. So we remember our Arrhenius equation from the previous slide. It was natural log of K equals negative activation energy over R times 1 over T plus natural log of A. So we need to be measuring the temperature and the rate constant in order to find the activation energy. So that is just what this example data set does. It's for this reaction of 2Hi gas goes to hydrogen gas and iodine gas. And this person has measured the rate constant K at a series of different temperatures, and then they've made a plot out of it. So we're going to pretend like we haven't seen this plot, because we know that this is not a plot of temperature versus rate constant. It's going to be a plot of natural log of rate constant versus 1 over temperature. We're going to have to make a transformation not only of the y data like we did for the integrated rate laws, but also of the x data. There's a lot of work that goes in before we can even make the plot. So we're going to just add some columns to our data set. We'll add a column for 1 over temperature, So its units are going to be 1 over Kelvin, Kelvin to the -1. And then we need to do natural log of K. And when we take the natural log of something, it doesn't really have any units anymore. You can't take the natural log of a unit. Okay, so we can plug this stuff into our calculator. If we take 1 over 555, we are going to get a really small number, 1.8 times 10 to the -3rd. We take 1 over 575, 1.7 times 10 to the -3rd. We take 1 over 645, 1.55 times 10 to the -3rd, 1 over 700, 1.4 10 to the -3rd, and 1 over 781, 1.3 times 10 to the -3rd. We don't have that many points this time, so it's okay to transform all of them. And then here we'll take the natural log of 3.52 10 to the -7. Going to get -14.9. Natural log of this number, -13.6. Natural log of this number, -9.4. Natural log of this number, you can see how this gets a bit tedious, -6.8, and natural log of 3.95, 10 to the -2, -3.2. So we've done our computation, we've transformed the data, so we're ready to make a natural log of K versus 1 over T plot. And you can see that the numbers in this plot should match up with the numbers we have. Let's check this last one. -3.2 is right here, and 1.3 10 to the -3rd is right here. And for the first one, -14.9 and 1.8 10 to the -3rd. So they have plotted all the same points that we have. They've just drawn the axes in kind of a weird spot. And so now our goal is to find activation energy. And so activation energy comes from the slope. It isn't equal to the slope, but it will come from the slope. So the slope of this line is going to equal negative activation energy over gas constant. So we know the gas constant, but we first have to find the slope. And we don't have the equation for this line, so we're going to have to find the slope. And in the beginning of this chapter, we talked about the different ways of finding the slope of this line. We can find the average slope by connecting the first and the last point. We can find the instantaneous slope between any 2 points, or we can find the initial slope at the very beginning. And since I sort of want to represent the entire reaction from beginning to end, I'm going to choose to do the average rate from the beginning to the end. So I'm going to use the first point and the last point. And we're going to do change in y over change in x, so change in natural log of K over change in 1 over temperature. All right, so slope is going to be equal to, we'll do this point at the bottom first, -3.2 minus the first point, -14.9 for our change in y, and for our change in x, 1.3 10 to the -3rd minus our first point, 1.8 10 to the -3rd. Here we go. And that should give us a very large negative number, -22,302. And since natural log of K doesn't have any units, and this inverse Kelvin is on the bottom, the unit for the slope is Kelvin, which doesn't make any sense because you can't have negative Kelvin, but that's just kind of part of how this formula works. So now this is our slope, and our slope is equal to negative activation energy over R. So -22,302 equals negative activation energy over the gas constant in the one with the joules in it, 8.314. This one is in Kelvin. This one is in joules per mole Kelvin. Okay, so all we have to do is solve for that one. The negative sign goes away, and our activation energy is 185,420 joules per mole. And this is a huge number, so I'm just going to go ahead and report it in kilojoules per mole, so it's a little bit more reasonable. There we are. So we used our linearized version of the Arrhenius equation. We plotted the natural log of K as the Y, 1 over temperature as the X, and then we did change in Y over change in X to find the slope. And then don't forget the last step, slope divided by that R constant. Okay, so we did it. It was a lot of work, but we did it. But you might remember that this looks kind of like something that we did way back in the solutions chapter. It looks a little bit like the Clausius-Clapeyron equation, where we said, what if instead of drawing this line, we could just connect 2 points into a formula? So let's make a slightly more usable formula that involves only 2 points. So we know that we only need 2 points to make a line. And it was very cool to use real data and to make a real line. But when we're doing it by hand and we don't have a spreadsheet at our disposal, it's really not that easy to get the slope for more than 2 points. So let's see if we can change the formula again so that we can relate it to just 2 points. All right, so here's where we're starting with. This is the linearized version of the Arrhenius equation. And so I want to try and adapt it so that it has 2 points. So I'm going to solve for the part that's constant and put it on one side. So I'm going to put the natural log of A on one side by itself. As soon as the document cam comes into focus. There we go. So I'm going to move everything except natural log of A to the left side. So natural log of K, we'll move this term. So plus activation energy over R over temperature. We'll leave natural log of A on this side. And so now if we want to adapt to 2 situations, we can say this is K1. Activation energy is always the same. The rate constant is always the same. We'll call this T1. And then we can set natural log of A equal to the same thing for situation 2. Natural log of K2 plus activation energy over R times 1 over temperature 2. So they're both equal to this thing. So that means we can set both sides equal to each other. We can rearrange them to collect like terms. So we'll try and collect all the terms with K on the left side and all the terms with T on the right side. So it looks a little bit more like the one we started with. So natural log of K1 minus natural log of K2 equals EA over R times 1 over temperature 2 minus EA over R times 1 over temperature 1. It's getting a bit clunky to carry around, but at least it makes a little more sense. And finally, we can simplify it by factoring like terms to get natural log of K1 over K2 equals, we can factor out an EA over R because that's the same for both of them. And then we have 1 over T2 minus 1 over T1. There we are, our linearized 2 situation version. So now we don't need to make the plot. And you'll notice this looks a lot like the Clausius-Clapeyron equation. The only thing that was different in that one is these were pressure values, and this energy value was a delta H of vaporization. But otherwise, it was the same sort of a relationship between energy and temperature and some other factor. Okay, so this is super cool because now we can do that same equation that we did on the transparency with the graph without doing the plot. So let's go back. Here's our plot. So let's try testing two different points to see if the math ends up the same. Let's try doing these points in the middle, 575 and 645. Because in theory, if this is a true line, any set of points that I pick should give the same slope. So we've got 575 and 1.22 10 to the negative 6. As our first points. And then for our second point, we're going to pick 645 and 8.59 10 to the negative 5th. Now it is real data, and so sometimes the slope isn't exactly equal because nothing is perfect in real life, but it should be at least fairly close. The slope between any 2 points that you pick should be approximately the same. And bonus, now that we've done this transformation of the Arrhenius equation to have this 2-point version, now we don't have to go to the trouble of finding 1 over temperature and natural log of K at the beginning. We can just do it as part of the equation. We can just plug them in as they are. So natural log of K1, that's going to be this one, 1.22 10 to the negative 6, over K2, which is going to be this one. Make sure you keep track of which one is 1 and which one is 2. So that equals activation energy we're trying to find. R constant is 8.314. 1 over temperature 2, which is 645. Make sure that's in Kelvin. And over T1, which is 575. And make sure you get the 2's and the 1's right. I always like to draw a line like this to remind myself that these 2 numbers need to be from the same case, and these 2 numbers need to be from the same case. All right, so from this point, it's just math. We can simplify this a little bit. That natural log term equals negative 4.25. And this temperature term is going to be negative 1.89 times 10 to the negative 4th. Very, very small number. So we're just solving here. And we should end up with an activation energy of positive 187 kilojoules per mole. Let's check that against our number from the model. When we did the average slope, we got 185 kilojoules per mole. And when we picked 2 different points, we got 187 kilojoules per mole. So it wasn't exactly the same number, but it was pretty close. So now we know how to find activation energy from a data set, how to find the slope and how to take the rate constant out of it, or to use this 2-point linearized version of the Arrhenius equation and plug in 2 different K values and 2 different temperatures. That is the end of the collision theory section.